So today we will learn about IP address lookup and packet classification in routers. In short, we will see how packet processing is performed in internet routers. So today our topic will be IP address lookup and packet classification in internet routers. Before actually we formulate the problem of IP address lookup in internet routers, we will first try to understand how addressing is done in the internet world. Now, as opposed to the telephone networks where the addressing is what is called as flat addressing, in internet we use a hierarchical addressing schemes. The reason being that in internet routers a decision to forward a packet is taken by looking at the destination address. By looking at the destination address, the router determines on which port the packet needs to be forwarded. Since the router may receive packets from any host and it may have to forward it to any other host in the world, it is therefore necessary that the routers must have the forwarding table for all the possible hosts which are connected to the internet. Now, this would make the forwarding table to be very large, and therefore the IP addressing scheme has been designed to be hierarchical. So, the IP addresses therefore are divided into two parts, a network number and a host number. Okay. So, we will see what are the properties of the IP addressing schemes. So, first of all, the IP addresses are globally unique. So, we have the property of these being globally unique, and second, which I was just discussing, is that IP addresses are hierarchical. In the sense that an IP address is divided into two parts. One is the network number and another is a host number. So, if you have an IP address, then it may be divided into two parts, one denoting the network number or network address, another one denoting it to be the host number. Now, with this hierarchical addressing scheme, the core routers, the intermediate routers or the intermediate nodes may have to store the entries corresponding to the network numbers only, and the node or the router which is directly attached to a particular host, it may have to store the entries corresponding to all the hosts which are attached to it, so that it can correctly forward the packets. This addressing scheme is something very similar to the addressing scheme that is used in post offices for posting the letters. For example, if somebody posts in New Delhi a letter which is addressed to me, let us say Abhay Karandikar, Department of Electrical Engineering, Indian Institute of Technology, Bombay, Mumbai, then the post office in Delhi just needs to see that the letter needs to be forwarded to the Mumbai city, and when it comes to the Mumbai city, then it looks that the nearest post office is a Powai post office. The letter will come to the Powai post office. Now, it is the Powai post office then really needs to figure out the exact addressee of the letter in order to deliver it correctly. Now, this kind of hierarchical addressing scheme leads to the scalability in the internet. That means a node can come up anywhere in the network without having it to register with all the possible routers in the internet. It needs to only register with its immediate router, okay, and the immediate router will contain the entries corresponding to all the hosts which are directly attached to it, and the packet will actually come to this immediate router since it belongs to the same network to which a particular host has been connected. So this kind of hierarchical addressing scheme has led to what is now called as an explosive growth in internet. One of the factors responsible for the explosive growth of internet is the hierarchical addressing scheme employed in the current internet. Now, when it was decided that IP addressing scheme will be hierarchical, it will be divided into the network number and the host number. Now, we know that the IP address is a 32-bit IP address. So therefore, possible nodes which can be there on the internet can be as large as 2 raised to power 32. Now, when we are going for dividing this 32-bit into two parts, one denoting the network number and another denoting the host number, clearly the question is that how many bits we should denote it to the network number and how many bits we should denote it to the host number. Accordingly, several classes of IP addresses have been defined. So let us study what are those classes of IP addresses. Class full IP addressing scheme. Earlier, it was decided that we can have a class A IP addressing scheme where essentially eight bits denotes the network number. 8 bits denote the network numbers in class A IP addressing scheme and 24 bits denote the host number. Now, if 8 bits are used to denote the network number, then the possible number of networks which can be there in the internet world can only be limited to 256. And soon, when this class A IP addressing scheme was introduced, it was realized that this is too few a number as the internet was evolving. So therefore, a class B IP addressing scheme was introduced. In class B IP addressing scheme, 16 bits are reserved for the network number and 16 bits are reserved for the host number. Now, the number of networks can be as large as 2 raised to power 16, which is some number like 65,000. And on each network, you can have as many hosts as 2 raised to power 16. Okay. So therefore, the class B IP addressing scheme was thought appropriate from the point of view of the fact that a number of networks were adequate. However, this led to a problem of IP address inefficiency, the usage of IP address inefficiency. For example, if you allot a network a particular 16-bit number as its network number, then this particular network consumes a block of 2 raised to power 16 IP addresses. Okay. That means the network can actually have 65,000 hosts on its networks because 16 bits are used to represent 16 bits are used to represent hosts on this particular network. Now suppose if this network just has some 5,000 machines. Just to give you an idea that if I use a class B IP address, some particular class B IP address, if I fix it, these 16 bits, then I can address 2 raised to power 16 hosts, which is approximately 64K hosts I can address. Now if I just have 5,000 hosts on the network, then my address inefficiency, so if there are only 5,000 hosts on the network, then my address inefficiency will be approximately 5,000 upon 64K, 65,000, some number, which leads to less than 1% efficiency. Right. This leads to around not less than 1%, around 5 to 6%, 6% efficiency, 6 to 7% of efficiency. So that means the IP addressing scheme is being used very, very inefficiently. The IP addressing scheme is being used very, very inefficiently if you are using class B IP addresses. Now to resolve this also, however, it was also found that the 16-bit therefore which are used to represent the host number appears to be too large a number, and therefore a new addressing scheme was designed which was called as class C IP addresses. Now in class C IP addresses you assign 24 bits for the network numbers and 8 bits for the host. Now this means then you can have large number of networks, okay, 2 raised to power 24 networks, but each network now is required to have only 256 machines. So now by using class C IP addresses we can actually address the problem of IP address inefficiency quite well. Just take the example that we have just taken, that suppose there are in a network which was earlier assigned a class B IP address, there were 5,000 machines. Now if I use a class B IP address, then as we have seen that my IP address inefficiency is 5 by 64. Okay, that is the efficiency with which I would be operating. The other way would be to look at that instead of having this one class B network, I can have as many as around 20 class C networks. Okay, if there are, and each class C networks having 256 machines. As a result, I would be able to address the problem of IP address efficiency quite well. But what will be the disadvantage? The disadvantage will be that since the number of networks, which was earlier only one class B network, and now there will be as many as 20 class C networks, since the number of networks has increased, the number of entries in the intermediate routers or in the core routers will also increase, and this will lead to an increase in the size of the forwarding table. So there is a trade-off that exists by using this classful IP addressing scheme. On the one hand, you have the danger of IP addresses being used inefficiently. On the other hand, you have an increase in the size of the forwarding tables. So one has to really find an efficient solution which addresses the problem of not only reducing the size of the forwarding table, okay, the size of the forwarding tables needs to be made more compact, because the memories ultimately will be used to store the forwarding table, and typically the cost of such memories in the core routers will tend to be very high, and which will make the cost of a router to be very high if the size of such forwarding tables is made high, is large. So we have to reduce the size of the forwarding table, and by reducing the size of the forwarding table also it helps us in reducing the search time when an IP address when a packet comes with an IP address. On the other hand, we would also like to use the IP addresses efficiently, because we just have 2 raised to power 32 IP addresses, and considering the fact that there is an explosion of hosts on the internet, we have to use judiciously the IP addresses. So with this, to balance this out, several schemes were proposed to address the problem of both the scalability in the internet should be maintained, the efficiency of the IP address space should be maintained, as well as the size of the forwarding tables should be reduced. So we have to address somewhat conflicting requirements from an IP addressing schemes. Okay. By the way, here I would just like to tell you that since 3 classes of IP addresses were defined, class A, class B, class C, when an IP address, when a packet comes with a destination IP address and we need to look, then the lookup is very simple. You first need to determine whether it is a class A IP address, or whether it is a class B IP address, and whether it is a class C IP address. And once you determine that it is a class A, class B, you can make pointer to the 3 different routing tables. So we may have 3 forwarding tables, each for class A, class B, and class C IP address, and then try to do so once you determine that it is a class A IP address, then you can do an exact match for the network number in your entry. So therefore the search operation is very simple. You have to first determine whether it is a class A, class B, or class C IP address, and then perform an exact match. Now, to distinguish whether it is a class A, class B, or class C IP address, what it is done is that in the class A, the first bit here is 0. So actually speaking, only 7 bits are used to determine the network number. So this first bit. So if we are employing a class full IP addressing scheme, and if the first bit happens to be 0, then it is a class A IP address. Similarly, in the class B IP address, the first 2 bits are 1 and 0. Okay. So which means only 14 bits are available to address the networks. So in the class A, actually the number of networks which can be there is really limited to 2 raised to power 7, which is 128 networks, and in class B the number of networks are really limited to 2 raised to power 14. Now since first 2 bits are 1, 0, they are used to represent the class B IP address. The class C IP address is indicated by first 3 bits being 1, 1, 0. Okay. So as a result, in class C, actually only 21 bits are available to represent a network. Okay. So remaining 3 bits are actually used to determine whether it is a class C IP address. So the algorithm would be that you determine whether the first bit is 0. So if the first bit is 0, then you know that it is a class A IP address. However, if the first bit is 1, then you search for the second bit. Okay, and the second bit happens to be 0, then you know that it is a class B IP address. And if the second bit happens to be 1, then you examine for the third bit. If it is 0, then it is a class C IP address, and if it is 1, then it is a class D IP address, which is actually used for the multicast purposes. But we are not going to discuss the class D IP addresses here. So So essentially, the first 3 bits is in search. In first 3 bits, you can determine whether it is a class A IP address, class B IP address, and class C IP address, and accordingly, you can go into the respective forwarding tables, perform an exact match, and determine where the packet needs to be forwarded. So the search operation is very simple if we are using a classful IP addressing schemes. But we just discussed that we yet to address the problem of scalability of the internet, efficiency of the IP addressing schemes, and keeping the size of the forwarding table simple. Now let us see how this problem was introduced, how this problem was addressed, particularly to resolve the problem of class B IP addressing schemes. Okay, so to resolve the problem of class B IP addressing schemes, which is that the 16 bits of the host numbers is too large a number. Okay, the concept of subnetting was introduced. So in subnetting, you are having another level of addressing hierarchy. Apart from the network number and the host number, and this is called as the subnet number. So what you do is that typically, in IP address, you have the network number and you have the host number. Now, if the entire network does not have, let us say, 65,000 machines, then what you do is that networks which are geographically together, treat them as one class B networks. Okay, so there may be 4 or 5 geographically co-located networks. You can treat them as one network as far as the outside internet world is concerned. They are one network. Now between them, what you can do is that this host number in 16 bits, you can divide them into subnet number and the actual host number. So what you can do is subnet number, subnet ID, and host ID. So for example, this 16 bit of the host number, you can divide it into 8 bits for subnet ID and 8 bits for the host ID. So for example, this could be 8 bits and this could be 8 bit. So as a result, what can happen is that, suppose that there are something like 200 geographically co-located networks are there, and each of these networks is having, let us say, about 200 to 250 machines. Then what we can do is that all these networks can be treated as one single network as far as the outside internet world is concerned. Now between them, we can distinguish each of these networks by their subnet ID, by these first 8 bits. We can distinguish each of them like that. And so basically what we can do is that when a packet comes, the router which is connected to all these networks, all the packets which are meant for any of the machines on any of these geographically co-located networks will get forwarded to the immediate router, which is the last hop for getting it connected to these geographically co-located networks. Now once the packet comes to this router will then determine from the subnet ID to which one of the subnets now the packet needs to be forwarded. Now this router will then forward the packets to that routers, the respective routers which is connected to the particular subnet. and then the subnet router finally will forward the packet to an appropriate host. Okay. Now the division of the host number into subnet ID and the host ID can be done by a network administrator. If there are just 4 subnets, then your subnet ID can be just 2 bits and your host ID can be 14 bits. Now this boundary is therefore variable, okay, and this can be identified by what we call as a subnet mask. Okay. So the network administrator can actually define what is called as a subnet mask, and that can be used to create the division of the host number between the subnet ID and the host ID. For example, in this particular case, you can have the subnet mask will consist of, in the network number and the subnet IDs, all ones, and here all zeros. So your subnet mask in this case could be 255 dot, in the decimal notation if we write 255.255.255.0. Okay. So this could be your subnet mask. Now this can to a large extent address the problem of IP address scheme inefficiency that has come because of the class B IP addresses, if you assign a full 16 bit to a particular network. So subnetting can actually address that problem to a large extent. Okay. The other extreme of addressing this problem fully is what is called as classless interdomain routing. Okay. So let me just explain what is a classless interdomain routing. Classless now, although the subnetting does address the problem of IP address inefficiency of the class B IP addresses, it still does not resolve the problem completely, because what you can have is really depends upon the fact that how many those geographically co-located networks are there which can be classified as subnet. Suppose there are 4 such networks only, then in that case you will require only 2 bits for the subnet ID, and then remaining 14 bits have to be there for the host ID. Now if there are 14 bits are there for the host ID, you can address as many as 2 raised to power 14 machines, and if each of these subnets has only 300 to 400 or 500 machines, then again you land up in the problem of the same IP address inefficiency. We are not using the bits which have been allocated to the host number in an efficient manner. So the ideal situation for the class B IP addresses scheme to get resolved completely by using subnetting is that you have as many number of subnets, and on each subnet these hosts are very nicely divided in such a manner that you can make a nice division of the host number into subnet ID and host ID, and then make use of the IP addressing scheme in an efficient manner. Now therefore it is required to have a new scheme, and classless addressing scheme was then introduced, which is now very prevalent today in the internet world. So let us understand what is classless addressing schemes, okay, which is also called CIDR, which is called classless interdomain routing. The basic idea of the classless interdomain routing is very simple. It stresses that the bits, remember that in the classful addressing schemes, fixed number of bits are used to represent the network number. That is 7 bits in class A, 14 bits in class B, and 21 bits in class C. So there are fixed number of bits which are used to represent a network number. The basic idea in the classless interdomain routing is that these prefixes which are used to represent the network numbers, they can be of any length. So the basic idea is that the prefixes should not be fixed 7 bits or 14 bits or 21 bits or 8 bits or 16 bits or 24 bits. They should not be fixed, but they can be of any arbitrary length. So the basic idea is that prefixes, the address prefixes can be of arbitrary length and not fixed. Now, how many bits will be used to represent that network number, that will actually depend upon what is the aggregation of various hosts into a network that is possible. Now remember that in classful IP addressing schemes the aggregation was fixed. It was either at 7 bits or 8 bits or 16 bits or 24 bits. Now here in the classless interdomain routing you can have aggregation at any level. Okay. So therefore aggregation can be performed at several levels, and not just as at the fixed boundaries. Now let us take up an example to explain these schemes. Okay. Consider, for example, 16 networks. These 16 networks are, let us say, 144.16.16.x to 144.16.31.x. These are 16 networks, and they are reachable through an ISP router. Now actually these are class B IP addresses, okay, and they may be reachable through an ISP router. Now if you look at these addresses, you will find that of course the first 16 bits are common in these IP addresses, but if you look carefully, actually the first 20 bits are common. Okay. So you can see from here observation that leftmost let us say that these are reachable through an IS. So leftmost 20 bits are common. Now typically in the forwarding table, since these are 16 separate networks, you would have had 16 entries in that ISP routers. But you recognize that all the 16 networks are reachable through a particular ISP router, and the first 20 bits of these addresses are common. So in that case, these 16 networks can be aggregated into one network, where the network number is this first 20 bits which are common to all the networks. So that means these 16 networks can be aggregated into a super network, and the forwarding table of the core routers now will have just one entry instead of having 16 entries, and that entry will be 144.16.16.20. This is represented by this. This means that if I write this in the binary notation 144.16.16, these are 24 bits, but the first 20 bits of this represents the address of this super networks. Now this can lead to not only the IP addressing efficiency, and I'll just explain how this can lead to the IP addressing scheme efficiency, but it can also, this can not only lead to an IP addresses efficiency, but it can also reduce the size of the forwarding table considerably. Look at this way, if instead of this class B IP addresses, this could have been class C IP address, which was 192.16.16. This could have been a class C IP addresses also. Now, as we were just saying, that suppose that there was a network which was having 5,000 hosts. Now, one alternative would have been to allot this network a block of class B IP address. If you do that, then we can have possible number of hosts as 2 raised to power 16. But this particular host has only 5,000 hosts. So therefore, as we had seen, the address inefficiency of 5 by 64. Instead of that, what we could have done is that this network of 5,000 machines, we could have divided into 20 class C networks, each networks having something like 250 machines. Okay, 250 into 20, that will be about 5,000 machines. We can have each of these networks to be a class C networks. Now, while allotting the addresses, what we could have done is that we could have allocated consecutive blocks of class C IP addresses. If I allocate consecutive blocks of class C IP addresses, okay, I can see that some of the bits in them will be common. So instead of therefore having 20 entries for class C networks, which actually increases the size of the forwarding table, I can do the aggregation not necessarily at 24 bits or 16 bits, but I can just find how many bits are common, okay, and then have only one entry in the forwarding table by representing it to be the address prefix which is common among all the hosts in the networks. So therefore, what is done in the classless interdomain routing is that, really speaking, the first bits which are common among all the hosts are used to represent the address of the network number, rather than the fixed 8-bit, 16-bit or at 24-bit boundaries. This can not only lead to the efficient use of the IP addresses, but can also reduce the size of the forwarding table. So that is the advantage of the classless interdomain routing. However, it does lead to some serious problem in the lookup search. Remember that when we were having classful IP addressing scheme, the search was very simple. There were 3 tables corresponding to class A IP addresses, class B IP addresses and class C IP addresses. All you need to determine whether the destination IP address is a class A IP address or a class B IP address or class C IP address. And once you determine that it is a particular class address, you just do an exact match in that forwarding table, and once the match is found, you will determine that on which output port the packet needs to be forwarded. So the search operation was extremely simple when we were employing classful IP addressing scheme. But with the classless IP addressing scheme, the search problem becomes little more complicated. Let me just illustrate with an example. Now, suppose you were earlier having the entries which we were just saying, 144 dot, or let us say take the example of class C IP addresses. Let us say we had this 192.14.16 to 192.4.31, right? So these were your 16 networks, okay, and you can see that they were aggregated to 192.14.16.20. Okay, first leftmost 20 bits are common. Now all these networks can be reached or reachable if you represent them by the first 20 bits. Now suppose out of these the network 192.4.21.x, it changes its ISP, and therefore it is no longer reachable through the same router through which these networks were reachable. So if that is so, then what we will have to do is that now the forwarding table will have two entries. Now has two entries. One is 192.4.1620 and another one is 192.4.21.24, because this now represents the complete IP addresses. Now what happens when a particular destination IP address comes, when a packet comes with a particular destination IP address that needs to be looked up? Unfortunately, it matches both the entries. Let us take a concrete case. Let us say that an IP address something like 192.4.17.192 it comes. Now this IP address, you can see that it matches the entry like 21, an IP address like 192.4.21.192 comes. Now remember that this host lies on this network, but it matches both the entries, because in this case also the first 20 bits are common. However, we know that this particular host lies on this network, and therefore a forwarding decision must be taken based upon this second entry. So what is the rule that we need to use? If a particular IP address matches more than one entry, then we need to select the longest match. Okay, we need to select actually the longest match. So this is what is called as the. So basically what we are saying is that some addresses will match both the entries or several entries, and we need to select the longest prefix match. So while classless interdomain routing has addressed the problem of IP address efficiency quite nicely and also has reduced the size of the forwarding table by allowing aggregation at arbitrary levels, it has led to a serious problem that the IP address lookup or the search is no longer exact match, but it is a longest prefix match. Now the longest prefix match therefore becomes one of the bottleneck in the forwarding performance of an internet router, and therefore there has been a host of research on developing algorithms for finding the longest prefix match in the shortest possible time, because the forwarding performance of a router depends upon determining the next hop by taking a decision based on the longest prefix match. So what we will be doing now is we will be studying some of the algorithms which have been used for the longest prefix match in an internet router. Okay. The solutions which have been proposed for the longest prefix match are both the software based solutions and second one is the hardware solutions. Typically, the software-based solutions will work like something like this, that there is a network processor to which a memory is attached, something like a network processor to an SD-RAM. The forwarding table is stored in this SD-RAM, and the network processor runs an algorithm. Whenever a destination IP packet comes, the network processor runs an algorithm and does a search in the memory and determines to which hop the packet needs to be forwarded. Now, various innovative algorithms have been proposed, and the crux of all these algorithms is to arrange the forwarding database in the memory in such a manner that the search becomes faster. Okay, so that is the IP address scheme which are basically implemented in a network processor in an internet router. The other schemes are hardware based, which are using either content addressable memory TCAM or specific ASICs or chips which have been designed to address the problem of lookup efficiently. So we will be discussing both the software based solution as well as the hardware based solutions. Now one important thing one must look up from the performances of an IP addressing schemes is there are two issues of the performance matrix of a lookup algorithm. One thing, of course, is that the algorithm should be having a very small search time. Okay, so it should be having a good search time. Typically, we need a wire speed performances of an IP lookup algorithm. So we are looking for wire speed performance. Second important thing is that when a route change occurs in an internet, this also gets reflected in the routing database. Now this routing database is really a database of these prefixes which have been stored. Whenever a routing change occurs, whenever this aggregation hierarchy changes, it reflects a change in the routing database. Now if a routing database change occurs, then your forwarding database therefore needs to be updated. Okay, and the performance of a lookup algorithm will also be determined by how much is the update time. On an average, it has been found that a route changes approximately 100 times a second. Therefore, the update performance of an algorithm must be of the order of few milliseconds. Okay, and the search time, of course, will depend upon what is the packet processing power that you are seeking from the IP lookup algorithm. If the interfaces happen to be the gigabit speed, then the lookup times must be in the microsecond or in the nanosecond range, the search time or the lookup time, and the update times could be of few milliseconds. So now that is the performance levels that we are seeking from an IP lookup algorithm. Okay, the lookup algorithm should also be scalable with respect to the number of prefixes. there was a heavy, when the classless interdomain routing was introduced, there was a considerable level of aggregation in the internet routers, and therefore the classless interdomain routing really reduced the size of the forwarding table. But today, we are seeing actually if there are shorter prefixes are there, then they actually represent more aggregations. Today we are seeing that the size of the routing tables are also exploding. There are many exceptions in the routing tables. Exceptions means where aggregations cannot take place, and therefore we need to store an entry separately. So therefore the size of the routing tables is also increasing, and therefore the performance of any IP lookup algorithm needs to be scalable with respect to the size of the forwarding table entries also. So we will look at the issues of the lookup time, the update time, and the scalability of an IP lookup algorithm with regard to the number of prefixes which are there. Typically, as I was pointing out in the internet routers, when a packet comes, the packet needs to undergo the IP address lookup, and then the packet needs to be classified into one of the classes. We will actually later on see that IP address lookup actually is a special case of packet classification. So a generic router will have a generic classification engine which can do the job of both the lookup as well as the packet classification. And special purpose processors are used to do these jobs, which have been actually optimized for doing this lookup and packet classification operations, and that is why they have been termed as network processors. So what we will do in the next lecture is that look up at some of the IP address lookup algorithms, both which can be implemented on the network processors, and some of the hardware architectures that have been proposed recently for performing the IP address lookup at wire speed.